Okay.
Trying to live together.
Okay. So, yeah, I'm a faculty member at the Penn State Astronomy Department. I'm going to talk to you about what to do with the little blips. Hello?
Yeah, you're good.
All right. What to do with the little blips that TESS finds that are transiting planets, or not. So just to set the scale of things, this is the terrestrial planets in our solar system. Everything looks familiar. Pluto is tiny. Earth and Venus are about quite similar. But we forget, even those of us working in this field can sometimes forget, that Jupiter and Saturn are a lot bigger, as are Uranus and Neptune. But the real scale of things becomes apparent when you add the Sun, and then you're trying to detect that little Earth-like planet around a monstrosity, a big star. And the transits are hard, and detecting it in velocity is equally hard. So what does the Earth do around the Sun? Over a year, we've all learned that planets go around stars. This is, of course, a lie. Planets and stars go around their center of mass. The stars tug on the planet, but the planets tug back on the star. The amplitude is very small because the stars are so much more massive. But we're talking about something like 9 centimeters per second per year of motion that the Earth pulls on the Sun. Very, very hard to detect. But we try very hard to do it. We do it with large prisms or large gratings where we disperse the starlight, and we look for what is basically subtle shifts of that starlight. Imprinted on the starlight are the absorption lines of each of the elements in its photosphere, and we can use those as markers. This is an example of the various types of things we can do. We can not only tell what the velocity of the star is, we can tell what the outer layer of the star is made up of. This is how we know what stars and planets are made up of. But when we talk about 10 centimeters per second, with any real astronomical instrument, this becomes borderline crazy. Because you're talking of how many atoms in my silicon detector is the motion that I need to detect. And it turns out that this is a few silicon atom lattices. So you can never do it with one line, but in aggregate, using thousands of lines, we actually do pretty well. So thermomechanical stability of your instruments becomes absolutely paramount to be able to do this. Because you really are against pretty much every law of physics at this point almost. Our gratings are big. How big? Pretty big. Our stars, here's this wonderful picture of a man walking a dog. The sun is this beautiful background. Well, real stars, including our sun, look like this. So we're trying to find a transiting planet, or the velocity of a planet, around a seething ball of plasma, which emits flares, which has spots, which has granulation in it. So these are very tricky, noisy sources, and we have to play all kinds of games to understand the astrophysics and tease out these signals. The other thing to remember is that we think of planets like our own, stars like our own, because of course we live here. But the most common stars in the Milky Way, and probably in most galaxies, are these dim, tiny stars called M-dwarfs. This is a little cartoon of what are the most common stars in a 10 parsec area around the sun, and you can see they're mostly M-dwarfs. There's a similar one very recently from Scientific American, which shows as the distance from the sun increases, what kind of stars do we see? Right up there is Alpha Centauri A and B and Proxima Centauri. Then you end up with Barnard Star and Lumen 16AB. And then as you go a little further away, you can see that the M-dwarfs are really dominant. So the M-dwarfs are the most common stars, both in the galaxy and in the solar neighborhood. M-dwarfs are red. They're just not painted red. Their temperatures are relatively low. Compared to the sun, they're about 3,500 to 3,000 degrees, while the sun is about 5,500 degrees. So we call these stars relatively cold stars, although they still melt iron in their photosphere, but they're cold stars compared to the sun. The other important concept is the habitable zone, which is in a cartoonish sense, the area around a star where liquid water can exist. So the area which is not too hot, not too cold, lovingly called, of course, the Goldilocks zone. Turns out that for the M dwarfs, the habitable zone moves inwards because the luminosity of these stars is pretty dim. At the same time, the transit depths are larger because the stars are smaller, and the stars are less massive, so the amplitude of the Doppler signal also grows. So in terms of detecting these planets, and in many ways characterizing them, M dwarfs are the place to look. They're the most common stars in the galaxy. They're the place where we can find Earth-like planets the easiest, or Earth-mass planets the easiest, and where we can do the characterization the easiest. So why aren't we looking there? Because very early on, the history of the field started with stars like our own, and it's only very recently with results from Kepler and now TESS that the field is sort of pivoted to saying, you know what, these are kind of interesting stars. We should really be looking around these stars. So we are building an instrument targeted towards the M dwarfs. This instrument is called the Habitable Zone Planet Finder, HPF for short. Here is HPF painted with laser light by Gudmundur Stephenson, who's there, on the largest optical telescope in the world, the Hobby-Eberle telescope, which happens to actually be a Penn State telescope. It's out in middle of absolutely nowhere, West Texas. It is 10.5 meters from point to point. It is a monstrous telescope in one of the darkest sites in the continental US. We're also building another instrument called NEID. This one goes on a telescope in Arizona called the Wind Telescope. And this one's more targeted towards stars like our own, sun-like stars. So when we talk about radial velocities, turns out it takes a lot of things to get this right. You need a telescope, you need a really good telescope, a lot of collecting area. You need to understand the atmosphere. You need to correct for the motion of the Earth around the sun. You need to worry about the fact that Ceres, the asteroid, is pulling on the Earth. And you have to get all that math right, which our pulsar astronomer colleagues have helped us out with a lot. You need to worry about fibers, calibrators, optics, stability of the instrument, and you need to have pretty advanced analysis codes and pipelines to be able to pull this data out. So we are building two of these instruments, and there are a couple of tricks we've played. One is to actually pull a very high vacuum so that you break the conductance of your optics with the outside. So those little air molecules that can jiggle around, you need to be at ultra-high vacuum before they don't jiggle around and short your instrument optics with the outside. We've built little radiation shields, little MLI blankets. I think Gumi is spreading around one that people can look at. Very complex technology. Mylar layers combined with bedding whale to break the thermal conductivity. I admit I went to at least one bridal expo to pick the right bedding whale. Turns out we picked the simplest one in the end, so I could have saved myself the trouble. HPF and NEID, two different telescopes, geared towards two different signs, but built on the same basic core R&D work that we have done here at Penn State. One is targeted towards dim M dwarfs, and the other is targeted towards solar-type stars. This is what the innards of one of these look like. Fairly complex, a lot of thermal control, lots of liquid nitrogen in there to keep things cold. But the punchline is we can keep the optics in there stable to 1,000th of a degree over long periods of time. And that took a couple years of working it out. This is what spectra from the Habitable Zone Planet Finder look like. And you can see we're talking about, tens of centimeters per second, and we can almost get there right now just from the instrument stability point of view. For the M dwarfs, we only need to be about a meter before we can find these planets. What is the HPF? HPF actually observes in what's known as the short wavelength IR. If you look at the inset shows you a visible image. You can see plants, there's some fog, there's no ship. You go into the 1 micron region, suddenly the ship appears and the fog kind of lifts and clears, you don't even see it. Anybody notice something funny about the plants? They're bright. Yes. Turns out that beyond 700 nanometers, in the real red, where our eyes cut off, plants glow. And there's been a couple of interesting thoughts about why that happens, whether the eye actually cuts off so you can see the tiger hiding in the plants, or whether it's just a coincidence, and we won't go there today. But that's called the red edge of vegetation. It's a clear signature of chlorophyll that can be observed from space in the unresolved Earth as a single pixel point. So HPF this is the picture of HPF leaving Penn State, because that's what you want to do with $5 million and 7 years of your life, right? Just put it on a, ship it off too. But you have to get into the telescope. So we did this last October, and fortunately it got to the telescope all in one piece and got installed beautifully, and it's now actually taking data, and we're getting great radio velocities on some of the M dwarfs. So what can spectroscopy give us? We talked about transits. Angie talked about transits, what TESS can do. But a transit is just a dip without the velocity. It tells you the radius of the planet, but not much else. Couple that with a velocity measurement, a dynamical measurement, and you get mass. Put mass and radius together, and suddenly you're talking geophysics or planetary geophysics, because you get planetary density. And you can make plots like this, which are planet radius versus planet mass. And you can tell, wait, is this just some puffy Neptune with an elevated atmosphere? Is this basically a ball of iron? Or is this a water world or an Earth-like density world? The error bars on these points are not super tight yet. But as we continue to observe and get more photometry and more radial velocity, they slowly, over time, will shrink and tighten. This is one of the core goals of TESS. TESS is a very rare NASA mission where its success depends on being able to do things like this from the ground, because TESS has to deliver masses and radii, and it can only deliver radii intrinsically. What else can spectroscopy give us? Well, it turns out during that transit, you can use the star essentially as a backlight and try to do spectroscopy of the outer planetary atmosphere. And turns out we've actually done this quite successfully. We can easily tell now whether planets have things like sodium, potassium, blue lines. We have a little bit more trouble, just because of the size of our telescopes, telling whether things have water, whether they have biomarkers. There's vigorous debate on what biomarkers are. Get 3 or 4 astronomers or planetary scientists in a group, and it's pretty sure there will not be consensus on what biomarkers are. It's a tricky problem. But the holy grail, as it were, is to get a spectrum of a planet transiting a star. And the only way we can do this in our lifetimes probably is with an M dwarf, transit-wise, and get things like oxygen, ozone, methane, and think about whether those things together tell us about the presence of life or not. But this is where the field is sort of pushing. Talking about some common or very interesting planets around M dwarfs. Some real, some fictional. There will be a quiz. Proxima Centauri. This one's actually real, we think. Recent discovery from a year or two ago. Nearest star to the Earth, nearest star to the Sun, and we think there is a planet in a 10-day, 11-day orbit around it. Very interesting. Doesn't seem to be transiting, but it certainly seems like the signal is real and there. Absolutely fascinating. Proxima Centauri might actually be in the habitable zone. We don't know what its mass is because it's not transiting, so it could be any inclination. Kepler-16, this is an interesting system that I've worked on some. Kepler-16, it's a Jupiter-like planet, so you don't expect to stand on its surface, but it transits an M dwarf and a K dwarf. Remind you of anything? So the joke, and this may not actually be a joke, it actually probably is real. When the Kepler team found Kepler-16, they wrote to Lucasfilms and said, hey, we found Tatooine. And the lawyers showed up the next day. Wolf 359. What famous fictional sci-fi event happened around the M dwarf Wolf 359?
The last stand of the Federation against the Borg.
Yes, the Battle of the Borg. Last stand of the Federation. Very good. Trappist one. This one's again real. It's not fictional. But it almost could be. 7 transiting planets around a late M dwarf. This is a star that is almost not a star. the radius of the star is just a little bit more than Jupiter. It's a very late type M dwarf. And when I talk about M dwarfs, it's a surprise to find 7 transiting planets around this. This tells us that planets and planetary systems around M dwarfs are very, very common. Statistically, from Kepler and from things like TRAPPIST-1, M dwarfs are just teeming with planets. The statistics are something like 2 planets per M dwarf in the galaxy. And there's a gazillion M dwarfs in the galaxy. Size comparison, this is very much like a Jupiter. LHS 2520. I would be very impressed if somebody gets this one. What famous character, fictional, LHS 2520? Well, so this is a kind of a recent occurrence, right? I don't remember this from when I was a kid, but this is recent, I think. Superman.
What?
Yeah. So turns out in Superman 14, which is actually a relatively recent comic from maybe a few years ago, they had him go visit Neil deGrasse Tyson, who has turned all the optical telescopes in the world into an interferometer so that Superman can observe LHS 2520 or Krypton blowing up. I don't know how we got here without the time delay, but it's very interesting. I think nobody under the age of 12 would have got this because I had not read this comic till but I can't really go on beyond this because M dwarfs are good enough for Superman. What else can you say, right? Thank you.
Don't the M dwarfs flare all the time?
The question is, don't M dwarfs flare all the time? Yes, turns out M dwarfs flare a lot. So the flare is a magnetic reconnection event that happens around all types of stars, but is especially vigorous around M dwarfs. And these flaring events can release a large amount of ultraviolet radiation and energy. This is still an ongoing debate. Turns out that if you have an ozone-rich planet, it will absorb most of the UV. Water on a planetary surface, you need a couple tens of centimeters or a meter of water before all that UV is gone. So flaring has often been talked about as, this kills life on a planet. The reality is we don't really know that much about life on planets. Certainly there might be ways in which we can eliminate the effect of flaring.
So all of these are ground-based instruments. Is it feasible at all, monetarily or just technically, to actually put one of these in space and get rid of any kind of atmospheric effects for detecting planets?
Okay, so the question is, of course, can we build a radio velocity instrument in space? For $10 billion, a lot is possible.
Telescope on the back, so
Tell us about the pronunciation.
So the question is, what is the pronunciation for the other instrument, NEID? And many of you may have been paid a little visit from the enforcer of the stickers, the little girl there. Ask her if you want stickers. There are HPF and NEID stickers. So the word NEID is a word in Pima, the language of the Tohono O'odham, and that reservation is where the Kitt Peak National Observatory is. In Pima, the word NEID means to discover or visualize. And when we were competing for this instrument, NASA told us to pick a name, so we picked the name that acknowledged the fact that it's a privilege to be able to do science on that reservation. So we picked a Pima word called NEID.
Okay, so with spectrographs, you can only look at about one star at a time. So if you don't have TESS or any Kepler or any of these other transit detecting satellites or programs, how do you pick which star you want to look at to see if it has a planet?
That's a very good question. So the radio velocity technique doesn't require there to be a transiting planet. You can go look around the nearest stars and find their planetary populations. You will not know precisely what the mass is because there's a ambiguity in what the orientation of the axis is. But you can still find those planetary systems. The transit is advantageous because you break that degeneracy, you get a very precise radius, and you are able to do things like transmission spectroscopy. But the radial velocity technique alone will find the planetary systems that the transit technique will miss because it takes a chance alignment with the transit, a very precise chance alignment, while the radial velocity is far less resilient on that chance alignment.